Jai Hind everyone. This is Naresh Kumar from Kumar Garg Engineering College, Ghaziabad. Welcome to the class of Optical Communication under Unit 5. In this video lecture, we will discuss two important topics, eye diagram and coherent detection. So first of all, the contents. So the contents for today's lecture will be introduction to the eye diagram, also known as eye pattern. Then we will discuss the eye pattern features in detail along with their meaning and significance. Then in the next topic, we will discuss the fundamental concept of coherent detection, and we will also differentiate the coherent detection with the direct detection. Then we will discuss the two categories for the coherent detection, that is homodyne detection and the heterodyne detection. So first topic is eye pattern. So basically main topic will be eye diagram. It is also known as eye diagram or pattern. Basically, the performance of any communication system is very important, and the performance of communication system will be same as that of receiver. If the receiver of the system is performing well, then the overall communication system is also performing well. So there can be different techniques or different methods that can be used for analyzing the performance of any communication system. In mathematical terms, there can be, for example, we may compute the performance in terms of bit error rate. We can also compute the performance in terms of probability of error. All these are mathematical forms, but the performance of any communication system can also be analyzed using some graphical method, graphical technique. So one such example of analyzing the performance using the graphs or diagram is eye diagram. And eye diagrams are basically the diagram or graph for any communication system in the time domain. So these are the graphs in the time domain for analyzing the performance of any communication system. And more specifically, the eye diagram are basically used for analyzing the performance of any wired communication system. And we know that optical communication is also an example of wired communication system. So eye diagram are nothing but these are the graphs or diagram in the time domain which are used for analyzing the performance of wired communication system, or for example we can say that optical communication system. Now why these diagrams are known as the eye diagram? These are called as eye diagram because of similarity in shape with the human eye. These diagrams are similar in the shape to the human eye. That's why these diagrams are known as the eye diagrams, or more popularly eye patterns. Now most importantly, we can analyze the distortion performance of the system using this eye diagram. By clearly seeing the diagram, eye diagram, we can comment about the distortion performance of the system. For example, if the eye is opened, then we will say that the distortion is less. And then if eye is closed or it is not properly opened, width and height of the eye are very small, then we will say that there is significant amount of distortion in the system. The next point is how an eye diagram can be generated. Basically, in the previous slide we have studied that the eye diagram is used for analyzing mainly the data handling capability, and distortion overall performance of the system by simply seeing the eye diagram. For example, if eye diagram is clearly opened, we will say less distortion, and if eye diagram is closed, we will say that distortion is significantly available. Now, how this eye diagram or eye pattern can be obtained? Basically, eye diagrams can be obtained for the system for which performance is to be analyzed by directly connecting that system signal which are under test, or the communication system which is under test, for example, optical communication system, that is connected with the standard BER test equipment. Standard BER test equipment. So, eye diagram can be obtained by connecting the system under test with the standard BER test equipment. Okay. So, any system for which we have to plot the eye diagram, that system under test is connected with a standard BER test equipment, and eye diagram is available on the display screen of the display device, on the display output screen. So, very simple procedure is there. If we have to test a system, that system signal is connected with the standard BER test equipment, and eye diagram is displayed on the output screen. Next is eye pattern features. Basically, in the eye diagram, there are a number of features that has very significant meaning. For example, amplitude distortion, timing jitter, rise time, we can tell about these. Moreover, due to interference, we can also tell. Let's see in the form of diagram. So, these are the two diagrams. One is eye diagram and second is its simplified form. This is the simplified configuration, and which is telling the meaning or significance of particular eye features. For example, in this case, one eye pattern feature is zero crossing. So this point is zero crossing. So basically this tells us about the threshold, about the threshold point VTH, whether the threshold is less or very high value. We know that in the receiver we have a decision circuit that compare the sample of the received signal magnitude with the threshold. If the sample magnitude is less than threshold, that is V is less than VTH, then decision is made in the favor of 0, that 0 is received, or otherwise decision is made in the favor of 1. So we can get some information about the threshold using this feature known as zero crossing. Then we have another feature or pattern, that is eye jitter. This is known as the eye jitter. This is denoted by delta T. So this eye jitter basically tells us about the phase distortion or phase noise. So this phase distortion or phase noise can be simply computed as delta T by TB into 100, where this TB is the bit duration. Next feature is width of the eye. This is the width of the eye width. So eye width basically tells us about the time interval at which the signal can be sampled without ISI. That is, in this duration, we can take the sample of the signal without inter-symbol interference. So this is the significance of width of the eye. Another important feature in the eye diagram is height of the eye. Okay, so this is the eye height. So this is the time interval in the width where the sample can be taken. But what is the best point where the best sampling time? So in the system, best sampling time is when the height of the eye diagram is maximum. So when the height is maximum in this point, so this is the best sampling time. Another important feature in the eye diagram is this slope of eye diagram. Basically, slope of eye diagram significantly tells us about the timing error. Timing error or synchronization related errors. So, as the slope becomes more and more horizontal, we can see that the eye gets closed. If the eye is closing, then the sensitivity towards timing error or synchronization error also increases, or overall performance of the system gets decreased. From the eye diagram, we can also comment about this. From point this, when the amplitude level is 20% to when this amplitude level is 80%. So this time when the signal level rises from 20% to 80%, this is known as the rise time. So from the eye diagram, we can also comment about the rise time of the system, which indicates the speed of the system. If the rise time is less, then we will say that. So we can also comment about the rise time. Another feature, we have this noise margin. We can also comment about the noise margin of the system, that is noise handling capability of the system. So in this case, we have voltage V1 and up to this point we have voltage V2. So ratio this V1 by V2 into 100, this indicates about the noise margin of the system. So it is clear that by simply seeing the eye diagram for the optical communication system, we can comment about the overall performance or overall distortion of the system. And there are a number of eye pattern or features which significantly explain the performance of the communication system. For example, another feature, simply seeing the eye diagram, we can also comment about the linearity of the system or linear characteristics of the system. If the eye diagram or eye shape is identical, if the eye diagram shape is identical and eye diagram is also symmetrical, we can say that the system is linear or system characteristics are linear. Otherwise, if the eye diagram is non-identical and non-symmetrical, we can say that the system is non-linear. So these are the various eye pattern features that we have discussed in the previous slide. Next is coherent detection. Basically, before studying the coherent detection, we will see that what is the meaning of detection. In the optical communication system, we have optical transmitter where signal is transmitted in the form of light. Then after passing through the fiber or channel, the light reaches to the optical receiver, and the receiver, we have the very first component, that is the photodiode or photodetector. So when the received light signal after passing through the fiber is incidented over the photodiode, the received optical power is converted into the corresponding electrical current. So when the optical power is incidented over the photodiode, it converts it into the corresponding photocurrent IP. So this process of converting the incidented optical power into the corresponding electrical form, optical to electrical conversion, by the photodiode or photodetector. For example, we can use either PIN photodiode or APD. This process is known as the detection. That is, received optical power is detected by the photodetector and it is converted into the corresponding electrical form, that is, photocurrent is obtained at the output. So, what do you mean by this coherent? Coherent means any technique that is employing non-linear mixing between the two optical waves. That is, basically we will have optical signal that is after through the fiber, after passing through the fiber, this one. Then we have an optical signal that is from a local oscillator or local source. These two optical signals are mixed in a non-linear manner and then incidented over this photodiode or photodetector. So this is the meaning of coherent detection. So in contrast, basically coherent refers to technique which make use the absolute phase of the incoming signal tracked by the receiver. That is, in this case, we also consider the frequency and phase of the signal along with the amplitude. So what is the need of coherent system? Basically, in the coherent system, we basically have two types of detection. One is direct detection and then we have the coherent detection. Direct detection and coherent detection. In the direct detection, we have the received optical power from the fiber is directly incidented over the photodiode or photodetector. This is the case of direct detection, where the received optical power is, as it is without any mixing, is directly incidented over the photodiode or photodetector. Whereas in the case of coherent detection, we have fiber, then we have this a signal from the fiber, then we have a local source, laser, and this is WLO. Power corresponding is PS corresponding to the signal and corresponding to local oscillator is PL. Then these two signals received from the fiber and from the local oscillator are coupled together, or mixing is done, and then it is incidented over the photodiode or photodetector, for example APD, and then it is converted into the corresponding photocurrent. So this is the basic difference between the direct detection and coherent detection. In this case, the previous signal received from the fiber is non-linearly mixed or coupled with the signal of the local oscillator, and then it is combinedly incidented over the photodiode or photodetector. And to ensure the improved sensitivity, we will ensure that the power of local oscillator is much greater than the power of the source. So there can be some simple difference, as we can see that this is simple, easy to implement, simple, easy to implement, and limited sensitivity. Whereas comparatively we can see that this is slightly complex, slightly difficult to implement, but most importantly, here we have limited sensitivity. Sensitivity of coherent detection is much better. So it is high sensitivity based system or better sensitivity. More importantly, in the direct detection, we use the principle of, for example, let's say intensity modulation and direct detection. So in this case, only we see the variation in the amplitude of the intensity of the light received. So we can say that it simply applies only the ASK. That is, FSK and PSK are generally not implemented. Whereas in the case of coherent detection, we consider both frequency and phase. So the coherent detection can be applied with ASK, FSK and PSK schemes. Whereas this direct detection can be applied only with when data rate or data transmission rate is less than 10 Gbps. Okay, so whenever 10 Gbps, then this direct detection cannot be applied. We can apply only the coherent detection. We also have some more advantages for the coherent detection, like spectral efficiency is better. Moreover, the impact of distortion as well as dispersion. For example, the tolerance capability for the intramodal dispersion as well as polarization mode dispersion is more or better for the case of coherent detection. So this is the need for coherent detection system, and after comparing we can see that in overall the coherent detection is better in terms of performance. So this is the detection method in the coherent system. As we have previously discussed, we have a received optical signal that is coming through the fiber. Then we have a local oscillator or light source, for example laser. So these two optical signals are coupled together with the help of a coupler, and then the combined signal is incidented over the photodiode or photodetector. As due to combination of the two signals, the incidented optical power gets increases, so the corresponding photocurrent achieved is also more. So it has the capability of detecting the weakest signal better as compared to the direct detection scheme. Then we have further the electronic processing part. Now let's see the complete diagram for the optical system that is applying the concept of coherent detection. So we can see that we have a message signal, then we have a carrier signal in the form of light, so laser is there. Then we can perform the modulation. That modulation we can apply either ASK, FSK or PSK. Then the signal is passing through the optical fiber cable. Then we have a local oscillator, and the two signals are then coupled together using the optical coupler, and the combined signal is incidented over the photodiode or photodetector. Then we get the corresponding photocurrent, and here we get the signal W1 minus W2, intermediate frequency. Actually, after coupling, we can get the signals either W1 plus minus W2. But if we consider W1 plus W2, in this case, the operating frequency range or the bandwidth will be more than the handling capability of the photodiode or photodetector. That's why we reject this case and we apply only the W1 minus W2. That is, if we use this case W1 plus W2, it is beyond the processing capability or range of the photodiode. So that's why we use only the difference intermediate frequency signal. Then this photocurrent may be weak. To amplify that, we use a front end amplifier. And then finally, to remove the noise, we use filter, and demodulation is performed to obtain the output data. So mathematical is there. So we have, this is the received signal part from the fiber. This is the corresponding signal from the local oscillator, and intensity of the combined signal that is obtained by combining the signal of, mixing the signal of source as well as local oscillator. So this is the corresponding intensity of the signal, mixed signal, which is incidented over the photodiode. This is the corresponding power, because we know that the power is directly proportional to the intensity. So this is the power signal. Now over this we can apply the concept of homodyne and heterodyne. Homodyne means when we have Ws equal to WLO, that is, we have intermediate frequency equal to 0. So in this case, proper matching is required for the signal received from the fiber along with the local oscillator frequency. So it is difficult. For that we will require PLL circuit or tuning circuit, but overall performance will get improved. So in the case of heterodyne, we will have Ws equal to non-zero, that is WLO. Both may be unmatched, matching is not required. So any optical source can be used along with the fiber as local oscillator. So in this case we have intermediate frequency as non-zero. So we can see that in the homodyne, when we have the intermediate frequency equal to 0, there is no frequency term. So there is no frequency term, so FSK cannot be applied there. We can apply only either ASK or PSK, and in this case the performance will be better, sensitivity will be more, but tuning circuit or PLL will be required. And last, in the heterodyne detection, the equation remains same, and we can see that clearly the phase term is there, frequency term is there, and magnitude term is also there. So in this case we can apply all ASK, FSK and PSK, and it is quite simple, as there is no requirement of matching, so we can use simply any optical source as the local oscillator in the receiver for the coherent detection, and no requirement of tuning circuit or PLL circuit. So that's all for this lecture. Thank you.